In this video, we're going to be talking about piecewise functions. And first off, let's define what we mean by a piecewise function. A piecewise function would be two or more functions. And here is the most important part, each with their own domain. So we're going to have, like example 1 here, you've got f of x is equal to each of these functions. However, they're equal to each of those functions at a different area. Like you're only equal to this function if the x value that you're plugging in is smaller than -3. You're only going to use this function if the x value that you're plugging in is between -3 and 7. You're only using this one if your x value you're plugging in is greater than 7. So that's what we mean by a piecewise function. So let's evaluate these. The first one says take f, plug in -5. So we've got to first find out where do we plug in -5. -5 is located in this first region right here. It's smaller than -3. So if you were to plug in -5, you would have to plug it in to the first function. So you have 2 times the absolute value of -5 minus 5, which is -10. So that'd be 2 times 10, which is 20. Second problem, f of 2. Let's again find out where 2 is located. 2 is between -3 and 7. So if you wanted to plug in 2, you'd have to plug it in here. Make sure as you plug it in, -x squared is -2 squared plus 4 times 2. -2 squared means take 2 and square it and then take the negative of it. That'd be -4 plus 8, which would be a +4. Finally, f of 7, anywhere greater than or equal to 7. We're going to plug it into this. So this will be pretty easy. F of 7 is the square root of 14 plus 6, which would be root 20. Instead of actually typing that into our calculator, let's just simply simplify it, split it into the square root of 4 times the square root of 5, which would be 2 root 5. Okay, number 2. Number 2 says find g of -3. First, identify where -3 is located. That would be between -4 and -2. Now, this one's easy because if you're located in between here, you don't even have to plug anything in. Anything in that interval is always equal to 8. B part says find g of -8. -8 is smaller than -4, so we've got to do 1/2 times, take out the x, plug in -8. That's going to be 1/2 times -8 to the third power is -512 plus 7. Half of -512 would be -256 plus 7 would be -249. And the last one, g of 3.1, we're going to use our floor function to evaluate it because 3.1 is bigger than -2. So we're going to do the floor function of 3.1 minus 4. Always do the stuff on the inside first. That's going to be -0.9. So we got to take -0.9, round it down to the next smallest integer, and that's going to be located at -1. Okay, now in the next section, we're asked to graphing piecewise functions. Graph each function, then give the domain, the range, identify the location, and types of discontinuity. Now, one way of graphing these, and this is not my favorite method, but one way of graphing these is by taking these x values and making a table of values, like plugging in -3, -2, -1 into my first table and making me a table for this, then doing the same thing for the second part. However, what I like to do is graphing these like normal and just knowing that I'm only supposed to graph the first part where x is less than 0. So I like to come over here to my graph and draw a division line. So where is less than 0? And notice this vertical line that I've just drawn. On your x-axis, that is 0. So the first part of my graph is only going to be graphed to the left of this. The second part of my graph is only going to be graphed to the right of this. Okay, so let's go ahead and graph the part to the left of 0. So let me erase this. Now the part to the left of 0 is an absolute value function. Now let me show you the easy way of graphing an absolute value function. This is a transformation that tells me where my vertex is going to be located. It's located left 1, 2, 3, and down 1. And then if you can get just a single point to the right or left of that, it's going to show you very nicely what the rest of those points are going to do. So what you can do is take, and I plugged in -3, that's where my vertex is located. So if you were to plug in maybe -2, if you find f of -2, that would be absolute value of -2 plus 3 would be the absolute value of 1 minus 1. And when you plug in -2, you get 0. So -2, 0 is going to be a point on your absolute value. Now, the slope or the slant, where this goes on this side is actually opposite of where it's going to go on the other side. So since you have a slope of up 1, over here you have a slope of minus 1. And you could just continue on. Now, let me show you a trick here. This is what I do if part of my graph is not in the domain, because I'm only supposed to be graphing to the left of this green line right here. And notice what happens on that green line. What about when x is equal to 0? We're only going to graph for everything less than 0. So as soon as you hit that green line, points are no longer part of your graph. So you're only going to graph this absolute value in this first section over here, not anywhere to the right of that green line. So what I'll do is I'll put open circles in there, because that tells me, well, once I hit that green line, those are no longer part of my graph. Now my graph continues on and on forever in this interval over here. So I'm going to put an arrow on the end, and then anything that's in the wrong interval, now I can come over here and erase. And now let's do the second part of our graph. Second part of my graph is a line, y equals 2x minus 5, and we're only going to graph that line over here. So anything that's on the line, since it's or equal to, I am going to include. So my y-intercept I'm going to plot first. So come down to 1, 2, 3, 4, 5. Do a solid circle because it is included. And then from there, you're going to rise 2 and run 1, rise 2 and run 1. And those are part of your graph, so I should be doing solid circles. And that's going to be it. Now, again, if for some reason you were to plot something over here, it would be an open circle. But my graph starts here and goes to the right and continues on forever. Anything that's not in my right spot, I'm going to erase. And you can actually erase the green line now that you're done. Your domain is what x values did you plug in. X can be anything less than 0 or greater than or equal to 0. It's your domain. Your graph extends left and right forever. You can also find domain by drawing a vertical line and moving it to the right and saying where all is my graph. And my graph is actually located everywhere since it goes forever. There's no breaks in my graphs, and my graphs does extend forever in both directions. So that's the reason, another reason why I have the domain I do. The range, notice there's no graph down here. Your y values start right here. And that's going to be at -1, 2, 3, 4, 5. And it starts with a closed circle. So my range starts at -5. And now let's see how far up it goes. I have graph here, 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 here. I've got graph here. And since these lines go up forever, there's no stop to my graph. So my graph extends from -5 all the way to infinity. Now, where is my discontinuity and what type is it? Notice that discontinuities, again, are x values. I do have, once I hit to this circle right here, it goes from here down to here. So at x equals 0, I have a jump discontinuity. If you don't remember the three types of discontinuity, the three types of discontinuity would be jump discontinuity, removable discontinuity to where you have just like a hole in your graph, and then infinite discontinuity. Number 4, same thing. Look at your divisions of your different intervals. You're going to graph this to the left of -3 and to the right of -3. So let me draw me a vertical line at -3 to keep it divided. The first graph that I'm doing is a line. That's going to be y equals -1x minus 4. Slope is 1, -1, and the y-intercept is -4. And I'm only going to graph it over here. So the way I'm going to do that is I'm going to plot my y-intercept, 1, 2, 3, -4. Notice I'm going to do it with an open circle because I'm not supposed to be graphing there. Then I've got a slope of -1. So that's going to be down 1 over 1 or up 1 left 1. No graph or any of those points. At -3, notice it says less than or equal to. So here I'm going to graph for anything less than or equal to -3. So I am going to include that -3 right there. And now I can continue on with my graph with solid dots. The first part of my graph is going to be this line. continued on forever, and I can now erase anything that was not part of my graph. The second part of my graph is a parabola that has not been shifted. So you can plug in 0 there, however you want to do it. Plug in 0, you're going to get 0. That's going to be the vertex of this parabola. And we can treat parabolas like we did absolute value functions. Parabolas are symmetrical. So if I can get a couple of points on one side, I can reflect it across that line of symmetry, which if you don't remember the lines of symmetry, that's negative b over 2a, to where here my b value is 0, my a value is 0, or my a value is negative 1/2, but that's going to give me an axis of symmetry of x equals 0. So now let's go ahead and plug in some points on each side of it. I'm actually going to plug 2 in. I'm going to find h of 2, and the reason I'm going to do that is because when I square 2, I know it's going to give me a 4, and it's going to be really easy to take half of that. So negative 1/2 times 4 will be negative 2. When I plug in positive 2, I get negative 2. And again, I can reflect that across my axis of symmetry to get another point. Now, I do want to plug in negative 3. I do want to see what happens at that point. Now, there's an issue here. If I plug negative 3 into this second function, now I do want negative 1/2 times 3 to the second. I get negative 4.5. Now, that's not going to be part of my graph. So what I'm going to have to do at negative 3, let's say go down to 1, 2, 3, 4.5. I'm going to have to do an open circle. That will not be part of my graph. However, when I reflect it over here, it will be. So there you see a good picture of my parabola. And again, you do want to go up to your line and see what's happening at that line, even if it's not included, so that you know what to do. You know where to place that point. Let me draw that a little bit better with an arrow on it. Okay, so now my domain includes all values less than or equal to negative 3 and greater than negative 3, so that'd be all values. Nothing is excluded. My range, this graph goes down forever, and there's no breaks in the domain breaks in the range, because here one graph picks up where another one stops right there, and then it goes up forever. So my range will also be all values. There's no horizontal line that I can draw that's not going to hit some point on the graph there. Discontinuities, again, you have from here to here, you have a jump. So that would be at x equals negative 3. You have another jump discontinuity. Okay, number 5. Your division for your domain here is at 1, so let's draw a vertical line at 1. Okay, everywhere to the left of 1 here, we're going to have to graph this. This is a transformation of your 1 over x function. You can to graph these, you can make a table of values if you need to. If you're not sure what this is going to look like, and plug anything in to the left of 1. So let's plug in a few points here. Let's plug in something easy. Let's plug in 0. When you plug in 0, you have 4 over 3, so you get 4/3. Let's plot that point. And notice I did a closed circle because it's in the right interval. You can even plug in 1. However, just be cautious, do I include it or not? And you are going to include it there. So when I plug in 1, that'd be 4 divided by 1 plus 3 is 4. 4 divided by 4 is 1. So when I plug in 1, I'm going to get 1. Plugging in a few more points, and I'll pause and plug those in and see what I get. Okay, here's where I plug the values in, and this is the graph I get. And it looks kind of funny if you don't remember what these graphs look like. But anywhere this bottom is equal to 0, we had what we refer to as an asymptote line. So here at negative 3, I've actually got an asymptote line that my graph is going to approach, and that's the reason it looks the way that it does. It's going to come up, and it's going to get closer and closer and closer to negative 3, but it's not going to touch it. Then the same thing is going to happen here on the other side. And I actually misplaced this point because that should be negative 4, negative 4. So 1, 2, 3, that one's there. So on this side, the exact same thing is going to happen. We're going to come down and we're going to approach and try to hit the points. We're going to come down and we're going to approach that line over and over and over. And then it's going to come up here somewhere and it's going to level off. Okay, and it looks like to me it's probably going to level off here at 0. So there's that side of the graph. Now let's look at the other side. and I can erase those asymptote lines when I finish. Now everywhere to the right of 1, I'm going to graph 2x minus 7, which is a simple line. So I'm going to come down to 1, 2, 3, 4, 5, 6, 7. I'm going to do an open circle. We're not including our division line here, so I'm going to rise 2, round 1. I'm going to put another open circle because that is not going to be part of it. And I'm wanting to graph this everywhere to the right. So now I'm going to start doing closed circles everywhere else. And my graph, when I connect the dots, will look something like this. So I can erase this circle here that wasn't part of it. My domain, notice where your breaks in the graph are. Now I do have a break over here in the graph at -3. X cannot equal -3 because that would be a 0 on the bottom. So my domain is going to be all values from -infinity up to -3. I'm not going to include -3. And then all values from -3 up to, ask yourself at 1, is x equal to 1? Yeah, you've got 1 as a possibility there. And then it continues on to the right forever. So I'm good everywhere else. My range, my graph comes down forever. And then I can start drawing these lines, and I'm hitting graph everywhere. Even here where I had this asymptote line, I'm going to hit graph over here. And there's no other parts of my graph to where I'm not going to hit something. So I'm perfectly fine everywhere from -infinity to +infinity as far as my range goes. Okay, discontinuity. Here at this asymptote line, again, notice that your graph on the left side and on the right side approach it, but I do have a discontinuity there, and that's called infinite discontinuity. Anytime you have that asymptote line, so an infinite discontinuity we'll do at x equals -3, and you also have a jump discontinuity. It jumps from here to down here, so it's going to be a jump discontinuity, and that was located at x equals 1. Number 6, my division lines are -4, 2. So let's draw those two lines. And there they are. Everywhere to the left, -4 is where you're going to plot the first part of your graph. So we're graphing 3x plus 8 if x is less than -4. Now, the only problem there is I need 1, 2, 3, 4, 5, 6, 7, 8. My y-intercept is located over here. Now I've got to use my slope, and I'm still not going to be in the right interval until I get to right here. And then the question is, do I include that point? Since it's or equal to, that is going to be a closed point. And then using my slope one more time shows me that that portion of my graph will look like this. Let's erase everything that was not in the right interval. Okay, for the middle interval, y is equal to -1. So no matter what your x value is, y is -1. That's going to be a horizontal line here. We're not going to include the -4 because of less than, but we are included the 2 because less than or equal to. So you have a horizontal line at -1 from there to there. And then you have this parabola that's been shifted right 2 and down 5. So that's going to be my new vertex. So 1, 2, 1, 2, 3, 4, 5 is the vertex. So it's going to be an open circle because it's not included. Now I do need some points on each side of that vertex to see what my parabola looks like. So I'd probably plug in maybe 3 here to see what that's going to look like. So let's do a little table of values, and let's plug in a value of 3. 3 minus 2 is 1. 1 to the second power is still 1. 1 minus 5 is -4. So when you plug in 3, I get -1, 2, 3, 4. It's not going to be part of your parabola, but there would be a point here as well. And maybe plug in one more value at 1, 2, 3, 4, and see what happens. 4 minus 2 is 2. 2 to the second power is 4. 4 minus 5 is -1. So when I plug in 4, I get -1. And there would be another point on my parabola here, but since that's in the region I'm not graphing, I'm not even going to put it over there, so I can erase that one as well. So you've got this parabola in this part of the region that goes up forever. So my domain now, and you can always pull your domain from the graph, or you can just look right here. You can plug anything less than -4 or equal to -4. You can plug in anything from -4 to 2, or you can plug anything greater than 2. And these functions have no discontinuities. Discontinuities are like division by 0 or the square roots of negatives and things like that. So there's no discontinuities, which you can tell also by your graph. The only discontinuities, excuse me, are the jumps and stuff like that. As far as breaks in the domain, there are none. However, the range, let's start drawing some horizontal lines and see there's graph here, there's graph here, there's graph there. There's nothing until I hit, there's question here. Well, I've got lots of graph here, and my graph extends forever upward. So we know we've got graph there. So I have graph everywhere. My range is from negative infinity to positive infinity. My discontinuities are both jump discontinuities. I jump from here to here, and I jump from here down to here. So I have jump discontinuities at x equals -4 and x equals 2. Number 7, my intervals, my breaks are at -1 and 2. I'm going to graph the first part of my graph everywhere to the left of -1. I'm not going to include -1. So therefore, it's going to be an open circle. And anytime you graph like y equals 7, that's a simple horizontal line. So 1, 2, 3, 4, 5, 6, 7, open circle. We're graphing everything to the left of that as a horizontal line. So there's the first part of my graph. The second part of my graph, which is going to be graphed in the middle, is x to the third minus 1. And you can plug in a couple of points, but you know kind of what that looks like. Plug in 0, you're going to get -1. Plug in 1, you're going to get 0. You can plug in 2, and it can be included because the less than or equal to, that'd be 8 minus 1, which is 7. So it's 1, 2, 3, 4, 5, 6, 7, which is located here and included. We can plug in -1, and we can include it on our graph, so it'd be a solid circle. So when I plug in -1, I get -1 minus 2, which is, or -1 minus 1, which is -2. So normally this graph would look something like this and come up, but we're only going to graph it from here inside. And that thing's going to go up to this dot. So there's the middle portion of our graph. And we did have some jump discontinuity from here down to there. Now the last portion of our graph is going to be the square root function. And we're going to graph it everywhere greater than 2. We can plug in 2. That'd be this negative square root of 4 plus 1. So that'd be -2 plus 1. -2 plus 1 is -1. So let's do an open circle at -1. And that's where my graph's going to start for that interval. Now let's plug in a few more points and see what that graph's going to look like. Now again, my advice, when you're plugging in points over there, make sure plug in some things that you know the square root of. Like I know the square root of 4, I know the square root of 9, so maybe you can plug in 4.5. I know that's something odd to plug in, but that'd give me the square root of 9. I know the square root of 16, so you could plug in an 8 so that when you do 2 times 8, you would get that 16. And those 2 points would be plenty enough. So let's plug those in and see what we get. So when I plugged in 4.5, let's see, 1, 2, 3, 4.5, I got -2. When I plugged in 8, I got -1, 2, 3. So that kind of shows me where my graph's going to go. It'll look something like that. So now let's look for any kind of breaks in my domain. And there are none. You can see there's nothing, no asymptote lines, nowhere that my domain is undefined. So we have all things from negative to positive infinity. My range, this graph does continue down forever, so you got to be careful there. The square root function does not have an asymptote line. However, I will have an upper bound on my range this time. So I'm going to go from negative infinity up to. Notice once we get to the top, my graph stops here and it flattens out over here. So there's no graph up here at all. There's no graph above 1, 2, 3, 4, 5, 6, 7. So my graph stops at 7. Now I am going to include 7 because here y does equal 7. That is part of your graph. And you only have jump discontinuity again. You have jump discontinuity at that -1 and that +2. So jump at x equals -1 and at x equals +2.